Okay, so with the z-score, right? So again, that tells you how many standard deviations the data value is from its mean. So in particular, if it's 0, then you have the mean value itself. So then you have the mean itself. A positive z-score means that that data value, right? For each data value, you can get a corresponding z-score. And if the z-score is positive, that data value is bigger than the mean. And if it's negative, it's below. That is, it's less than the mean. And again, for normal distributions, for data values, you can calculate the corresponding z-score and work with the standard normal distribution curve. Here, in particular, let's look at the empirical rule for standard normal distribution. Instead of going to the normal distribution, subtracting the standard deviation, subtracting 2 times the standard deviation like we've been doing, you can just convert to the z-score and consider this. In the standard normal distribution, because the z-score is, the standard deviation is 1 and the mean is 0, that tells you 68% of all the z-scores, of all the data values in the standard normal distribution are between 1 and -1. 95% are between 2 and -2. 99.7% are between 3 and -3 of the data values in the standard normal distribution. In particular, a z-score, okay, if it's below -3 or bigger than 3, it's an unlikely value. I mean, it's possible, but it's really not likely to occur. Okay, good. And again, to go back and forth between a data value and its z-score, we're going to use this formula. Okay. But let's do an example. So let's suppose we have a test, right? We have the data from a test out of 15. We have the test scores, that is. It turns out those data values, those scores, they're normally distributed with a mean of 8 and a standard deviation 2. So we have these test scores, right, from a test that students took. The exams are out of 15. Okay, they're out of 15. And it turns out those data values, those scores, they're normally distributed with a mean of 8 and standard deviation 2. So instead of working with those scores directly, we can look at the corresponding z-scores, which makes things a little bit easier. For instance, let's suppose a student gets a 5 on the test. What's that z-score? Well, using the formula here, we replace x by 5. The mean we're given is 8. The standard deviation is 2, as you can see. So we have 5 minus 8 over 2. And what's that equal to? 5 minus 8 over 2? That's -3 over 2, which is -1.5. So the z-score is -1.5. And that tells you right away that the student's the student's exam score, is about 1.5 standard deviations to the left of the mean. Okay, so that's what we expect here. Okay, that's good. And okay, so we have that example. So we get here. Now, for this one, here's another one. We can actually go the other way. You know, before just now, we took the exam score and found the z-score. Now, let's go the other way. Namely, if I give you a z-score, also called a standard score, right? Remember, here it is, a z standard score, z-score, same thing, right? We can get the corresponding data value. Basically, here what's going to happen is we're going to replace z with our 2.5. We're going to solve for x. That's what we're going to do. We're going to solve here for x. Okay, that's good. So let's do it. So we have 2.5 is x minus 8 over 2, but we want to solve for x now. I mean, the x usually goes on the left, the unknown is on the left-hand side. So that's why we have x over here. And we want to solve this equation for x. So we want to solve it for x. Okay. So what do we do first? Well, as I have over here, we can eliminate this denominator of 2 by multiplying both sides by 2. When you do that, these 2's are going to cancel. We get x minus 8. On the right-hand side, we have 2 times 2.5. I know 2 is on the left side here, but again, you can multiply in any order you want. So it really doesn't matter which side it's on. But 2 times 2.5 is 5. So we have x minus 8 equals 5. That's good. So what? Well, we want x, right? So we add 8 to each side. We get x is 13. So the test score that corresponds to a z-score of 2.5, standard score of 2.5, is 13. So we're going back and forth like this between data values and z-scores. And the z-scores, I should say this, those are data values on the standard normal distribution. Not sure if I said that, but these are just scores. These are data values on the standard normal distribution, z-scores. Okay. We had this example. Let's do another one. Well, no, we just did that. Sorry. I want you guys to try this one. So basically here, we're given that the weights of a certain dog breed, they are approximately normally distributed, and the mean is 62, and the standard deviation 6 pounds. So basically the weights, the data here, which is the weights of the dog breed, that's normally distributed with a mean of 62 and standard deviation 6. That's all. And what I want everyone to try now is, 5 minutes, it's going to be kind of close. I guess we should just do it together, actually. We're getting low on time. But normally what I want everyone to do was to get the z-score for the weights. So let's do that together, though, since we're low on time. So for the first one, 55 pounds, we want to know what the z-score is. Okay, now, so what do? We use the formula. Here we're given x. We want the z-score, so we don't know what z is. So we have 55 minus the mean over the standard deviation. The mean we're given is 62. The standard deviation is 6. So we have the mean minus the standard deviation. Excuse me, we have the data value minus the mean over the standard deviation. So we get this. We get negative 7/6. You know, you can round it to get about negative 1.17. So in other words, the z-score for this value of 55 pounds, it's about negative 1.17. I mean, again, I know, like, I tried to explain, hopefully I was successful, I don't know if I was, with why we calculate z-scores. We'll see more about why next time, but let's keep going with this example. But from here alone, we can see that the z-score is negative 1.17. So 55 pounds, that's going to be to the left of the mean, and it's going to be about 1 and 0.17 standard deviations less than the mean. In particular, if we went back to the slides here, we know a z-score below negative 3 and above 3 or above 3. You know, those scores are very unlikely. Those are very